Welcome to our deep dive into low-temperature physics.
Yeah.
It's going to be fun.
Yeah.
Today, we're going to be exploring matter at
Okay.
extreme cold, and we're going to be using excerpts from a National Geographic article about the physicist Lev Landau.
That's cool.
So get ready to be amazed as we kind of uncover how pushing the limits of cold revealed a whole new world of quantum phenomena.
Right.
From superfluidity to superconductivity, we're talking liquids that flow without any resistance.
Uh-huh.
And materials that repel magnetic fields.
Yeah.
All thanks to the mind-boggling world of quantum mechanics.
It's truly a realm where our classical intuition breaks down.
Right.
And we enter a world that's governed by the strange and beautiful laws of quantum physics.
Yeah, so to kind of kick things off,
Okay.
let's get to know Lev Landau,
Oh.
this physics prodigy.
Uh-huh.
The article mentions that he entered university at the age of 14.
Wow.
I can't even imagine having that level of intellectual firepower
Right,
at such a young age.
Landau's precociousness was legendary. He was born in 1908,
Yeah.
and he displayed an exceptional aptitude for mathematics.
Yeah.
And a remarkable confidence bordering on arrogance when it came to tackling complex physics problems.
Huh?
In fact, he once quipped that he could have contributed to the development of quantum mechanics
Okay.
had he been born a few years earlier.
Wow, that's some serious ambition.
Right.
But it wasn't just bravado, was it?
Oh, no.
He actually made significant contributions
Yeah,
to quantum physics.
absolutely. Even as a young man, Landau was already making waves in the field,
Okay.
particularly in understanding the behavior of electrons in magnetic fields. He was deeply fascinated by the revolutionary ideas emerging in Europe at the time.
Okay.
Things like relativity and quantum mechanics.
Uh-huh.
He yearned to be at the forefront of these groundbreaking discoveries.
Yeah, it makes sense that he felt he might have missed out.
Right.
Quantum mechanics was a paradigm shift.
Yes.
It completely changed how we view the microscopic world.
Indeed. It revealed that at the atomic and subatomic level, energy comes in discrete packets called quanta.
Yeah.
Particles can behave like waves.
Wow.
And there's a fundamental limit to how precisely we can know both a particle's position and momentum.
Okay.
It was a truly revolutionary era in physics.
So to understand why Landau's work is so significant,
Okay.
we kind of need to delve into why extremely low temperatures are so crucial for observing these quantum effects.
Okay.
Most of us will never experience anything close to absolute zero in our daily lives.
Right.
So why does it even matter?
That's the beauty of it.
Yeah.
At everyday temperatures, the chaotic thermal motion of atoms kind of masks these delicate quantum phenomena.
Okay.
However, as we cool things down, that motion quiets and the quantum nature of matter takes center stage. Imagine turning down the noise to hear a faint but beautiful melody.
Right.
That's what reaching ultra-low temperatures allows us to do,
Okay.
to hear the subtle whispers of the quantum world.
So by cooling matter down to extreme temperatures, we're essentially opening a window into this hidden quantum realm.
Precisely.
And it was this realm that captivated Landau.
Yeah.
He was particularly drawn to a substance that defied classical expectations entirely. Liquid helium.
Yes.
Ah, liquid helium.
Yes.
The stuff of science demonstrations and superhero origin stories.
Right.
But seriously, what makes it so unique?
Well, for starters, it remains liquid even at absolute zero.
Okay.
The lowest possible temperature, which is negative 273.16 Celsius or 0 Kelvin.
Right.
Classically, everything should freeze solid at absolute zero, but helium stubbornly refuses.
Okay.
That's because quantum mechanics is at play.
So you're saying that even at absolute zero,
Yeah.
there's still some motion.
Exactly.
That's mind-boggling.
This is due to a concept called zero-point energy,
Okay.
which arises from the Heisenberg uncertainty principle.
Uh-huh.
Even at absolute zero, we can't know both the position and momentum of an atom with perfect accuracy. This inherent uncertainty leads to a minimum energy state,
Okay.
preventing atoms from completely stopping their motion.
So it's like the atoms are always doing a little jig,
A perfect analogy.
even in the deepest freeze.
But with liquid helium, the story gets even more fascinating. As we cool it down below a specific temperature called the lambda point,
Okay.
something truly remarkable happens. It transitions into a new phase called a superfluid.
Okay, this is where things get really mind-blowing.
Right.
Superfluidity.
Yes.
I've seen videos of liquid helium crawling up the sides of containers. It's like it's breaking the laws of physics.
It's one of the most dramatic demonstrations of quantum mechanics on a macroscopic scale.
Yeah.
Picture this. Liquid helium flowing without any viscosity,
Okay.
meaning it experiences zero friction.
Wow.
It can squeeze through the tiniest cracks, climb walls, and defy gravity.
So it behaves completely differently from how liquids normally behave.
Yes.
Like, imagine trying to pour honey through a tiny crack. It wouldn't work because of its thickness and resistance to flow,
Exactly.
but superfluid helium would just glide right through effortlessly.
Exactly. The absence of viscosity means there's no resistance to flow.
Right.
And this remarkable phenomenon is directly tied to the quantum world.
So how did Landau explain this crazy superfluidity?
Okay.
What was his take on it?
Landau wasn't convinced by the early attempts to explain superfluidity using the analogy of an ideal Bose gas.
Uh-huh.
These models, like those proposed by Fritz London and Laszlo Tisza,
Okay.
seemed too simplistic to him.
Yeah.
Landau felt they didn't capture the complex interactions happening within the liquid.
So we had a different approach.
He did.
Okay.
Landau's key insight was to link superfluidity to the absence of energy dissipation.
Okay.
His reasoning was elegant. If there's no viscosity, there's no friction.
Uh-huh.
So the liquid can't easily lose energy by creating disturbances.
Okay.
He called these disturbances elementary excitations.
So it's like the superfluid is in a state of perfect flow, unable to create any ripples or waves.
Right.
Because it can't lose energy through friction.
Precisely.
Okay.
And to further solidify his theory, he went on to propose a model for the energy spectrum of these excitations in the superfluid.
Okay.
He distinguished between phonons, which are essentially sound waves,
Yeah.
and rotons,
Okay.
which he envisioned as tiny swirling vortices within the liquid.
He just envisioned these tiny vortexes.
It was pure intuition.
That's remarkable.
But later experiments confirmed these ideas,
Wow.
solidifying Landau's theory.
Yeah, that's the kind of genius we're dealing with here.
Right.
He could intuit physical phenomena that were later proven correct.
Yes.
Now, to fully understand Landau's contribution to superfluidity,
Okay.
we need to talk about another fascinating quantum phenomenon. Bose-Einstein condensation, or BEC.
Okay.
Okay, I'm ready for more mind-blowing quantum concepts.
All right.
What is BEC, and how does it relate to superfluidity?
Imagine a group of particles called bosons.
Okay.
These bosons have a unique characteristic. They like to be in the same state.
It's as if they all want to play the same game.
Right.
As you cool these bosons down to extremely low temperatures, they start to occupy the lowest possible energy state,
Okay.
forming a single coherent entity known as a Bose-Einstein condensate.
So they all become one big entity behaving in unison.
Exactly.
Yeah.
They all share the same quantum state.
Yeah.
Now, while both superfluidity and BEC are quantum phenomena, they're not the same thing.
Oh.
It's a crucial distinction.
So there's a difference.
Yes. For
Yes.
example, an ideal gas of bosons that forms a BEC wouldn't actually be superfluid.
Oh,
It needs interactions between the atoms
okay.
to achieve that frictionless flow we see in liquid helium.
So BC is necessary but not sufficient for superfluidity.
Precisely.
Okay.
And while Landau's theory beautifully explained superfluidity, it was Richard Feynman who later provided a more microscopic understanding.
Okay.
Building upon Landau's insights,
Oh.
showing how the interactions between helium atoms lead to the observed behavior.
So teamwork makes the dream work.
Yeah, even in physics.
Okay.
But wait,
No.
the title of our deep dive also mentions superconductivity.
Right?
Is that related to all this superfluid stuff?
Yes.
It seems like we're moving from one mind-blowing phenomenon to another.
What's fascinating is the connection between these seemingly disparate phenomena. Superconductivity is another macroscopic quantum effect observed in certain materials at low temperatures.
Okay.
These materials exhibit zero electrical resistance, meaning electricity flows through them with no loss of energy.
Oh, wow.
They also expel magnetic fields, a phenomenon known as the Meissner effect.
So it's like superfluidity, but for electrons instead of atoms.
In a way, yes.
Okay.
And it turns out Landau played a significant role in developing the theory of superconductivity as well.
Okay.
He collaborated with Vitaly Ginzburg to create a theory that beautifully captured the essence of this phenomenon,
Wow.
using an approach remarkably similar to his work on phase transition.
This is incredible. It seems like Landau's work was instrumental in bridging the gap between the macroscopic world we experience
Right.
and the microscopic quantum world.
Absolutely.
This is definitely a lot to process.
Yeah.
Maybe we should take a moment
Yeah.
to let our listener digest all this amazing information
Yeah.
about superfluidity, BEC, and the early hints of superconductivity.
A good idea.
Yeah.
We've covered a lot of ground, and when we return, we'll dive deeper into the world of superconductivity
Yeah.
and explore how Landau once again played a pivotal role in unraveling its mysteries.
Okay. Sounds good.
All right.
Welcome back. I hope you had a chance to maybe catch your breath because we're about to plunge even deeper into this quantum realm
Okay.
as we explore superconductivity,
Right.
a phenomenon that's just as mind-boggling as superfluidity.
It's truly a testament to the strangeness and beauty of the quantum world.
Before the break, you mentioned that Landau and another physicist named Ginsburg
Right.
developed a theory to explain superconductivity.
Yes.
Can you tell us more about that?
Yes. Ginsburg and Landau used a clever approach building on Landau's earlier work on phase transitions,
Okay.
like how a magnet loses its magnetism when heated above a critical temperature.
Right. He introduced that concept of an order parameter,
Exactly.
a variable that changes as the system transitions between different phases.
Exactly. Ginsburg and Landau realized that the transition between a normal state and a superconducting state could also be described using an order parameter.
Uh-huh.
Their genius was in choosing the right one, an effective wave function,
Okay.
to represent the superconducting electrons.
Okay, now we're getting back to the quantum world with wave functions.
Right.
Remind me, why are wave functions important
Okay.
when we're talking about electrons?
Well, remember that electrons have both particle-like and wave-like properties.
Yeah.
In a superconductor, these electrons pair up to form what are known as Cooper pairs.
Okay.
These Cooper pairs act like bosons, and Ginsburg and Landau's theory described how these pairs condense into a single macroscopic quantum state.
Wow.
The key to superconductivity.
So similar to the Bose-Einstein condensation we talked about with superfluidity.
Yes.
But now it's pairs of electrons doing the condensing.
A brilliant observation.
That's pretty cool.
And just like with superfluidity, the interactions between these Cooper pairs are crucial for explaining the unique properties of superconductors,
Right.
such as zero resistance and the expulsion of magnetic fields.
This is fascinating.
Yes.
Ginsburg and Landau's theory essentially connects the macroscopic behavior of superconductors to the microscopic world of quantum mechanics.
Precisely.
Wow.
Their theory, published in 1950, predicted a whole range of superconducting phenomena that were later confirmed through experiments.
That's amazing.
It was a major triumph for theoretical physics.
Yeah.
And it earned Ginsburg a share of the 2003 Nobel Prize in Physics.
Unfortunately, Landau wasn't there to share that prize.
Sadly, he passed away in 1968.
Yeah.
However, the Ginsburg-Landau theory remains a cornerstone of our understanding of superconductivity. It highlights Landau's extraordinary ability to develop powerful theoretical frameworks to explain complex phenomena connecting seemingly disparate worlds.
It's amazing how his work continues to shape our understanding of physics, even decades later.
Yes.
But the source material also mentions something called the BCS theory.
Right.
Was that another attempt to explain superconductivity?
Yes. The Bardeen-Cooper-Schrieffer theory, or BCS theory, came a few years after the Ginsburg-Landau theory
Okay.
and provided a more microscopic explanation of superconductivity.
Right.
It focused on how interactions between electrons and vibrations of the crystal lattice lead to the formation of those Cooper pairs we talked about.
So BCS dug deeper into the mechanics of how these electron pairs form and why they behave in such a unique way.
Exactly.
Okay.
It was a groundbreaking achievement that earned Bardeen, Cooper, and Schrieffer the 1972 Nobel Prize in Physics.
Wow.
And here's what's even more remarkable. Despite their very different approaches, the Ginsburg-Landau theory can actually be derived from the microscopic BCS theory.
Wow, that's a fantastic example of how different levels of explanation in physics can ultimately converge.
Absolutely. It speaks to the interconnectedness of the physical world and the power of theoretical frameworks to reveal these connections. Now, shifting gears a bit,
Okay.
Landau's contributions to the study of matter at low temperatures didn't stop there.
Uh-huh.
He also developed a profound theory to describe what are known as Fermi liquids.
Fermi liquids. What are those?
Well, remember how we talked about the surprisingly effective model of electrons in a metal as an ideal gas of fermions?
Yes. Even though electrons are charged and should interact strongly with each other, the ideal gas model does a pretty good job of capturing many of their properties.
Right. But Landau, as always, wasn't content with just knowing that it worked. He wanted a deeper understanding of why.
Okay.
This led him to develop the theory of Fermi liquids, a framework that took into account the interactions between electrons in a more sophisticated way.
So he was looking to create a more accurate model going beyond the simplified picture.
Precisely. He realized that while the interactions between electrons are strong,
Yeah.
they don't drastically alter the overall energy levels of the system.
Uh-huh.
So instead of treating electrons as individual particles, he introduced the concept of quasi-particles,
Okay.
representing the collective excitations of the interacting electron system.
It sounds like he was trying to find a way to incorporate the effects of those interactions without completely throwing out the useful parts of the ideal gas model.
That was Landau's genius. He could cut through the complexity and identify the essential physics. He then developed a phenomenological approach, meaning he didn't try to calculate the interactions from first principles. Instead, he introduced a small number of parameters that captured their overall effects.
So instead of getting bogged down in the details of every single electron interaction, he found a way to characterize their collective behavior with just a few key parameters.
Exactly. This seemingly simple approach turned out to be incredibly powerful. Landau's Fermi liquid theory provided a more accurate description of the properties of real liquids, including helium-3,
Okay.
the fermionic isotope of helium.
Okay, so we have helium-4, the boson, which exhibits superfluidity. And now we have helium-3, the fermion. Does it behave differently at low temperature?
It does.
Okay.
And Landau's Fermi liquid theory provided the framework to understand its behavior.
Wow.
Helium-3 doesn't become superfluid at the same temperatures as helium-4 because, as we discussed, fermions can't all occupy the same quantum state.
Right.
However, it turns out that helium-3 does become superfluid,
Okay.
just at much lower temperatures.
Another example of how quantum mechanics can lead to unexpected and fascinating behavior.
Yes.
So Landau's theory helped us understand both types of liquid helium.
Precisely. The discovery of superfluidity in helium-3 in 1972 was a major triumph for low-temperature physics, further cementing Landau's legacy as a pioneer in this field. His theoretical framework, developed decades earlier, provided the foundation for understanding this remarkable phenomenon.
It's clear that Landau had a profound impact on physics.
Yes.
From superfluidity to superconductivity to Fermi liquids. His work has truly shaped our understanding of matter at the most fundamental level.
Indeed. His ability to see the underlying simplicity in complex systems and to develop powerful theoretical tools to describe them is a testament to his extraordinary genius.
Now, I'm really starting to grasp why he's considered one of the greatest physicists of the 20th century. But the source material also mentions his 10 Commandments.
Right.
And this intriguing minimum theoretical program he developed. They sound almost mythical.
They do, don't they?
Yeah.
These aspects of Landau's legacy reveal not only his brilliance as a physicist, but also his unique approach to teaching and shaping the next generation of physicists.
Well, I'm definitely intrigued. Before we move on to that, though,
Okay.
let's give our listener a moment to ponder the incredible world of superconductivity and Fermi liquids we've just explored.
Yes, let's pause here for a moment. When we return, we'll unravel the final pieces of the puzzle and delve into Landau's 10 Commandments and his theoretical minimum, which played a significant role in shaping the landscape of theoretical physics.
Welcome back. We've been on quite a journey through low-temperature physics, exploring these mind-boggling phenomena, superfluidity, superconductivity. Yeah. We even delved into Fermi liquids. Now I'm really eager to learn more about those 10 Commandments.
Yes.
And this theoretical minimum program you mentioned. They sound almost mythical.
They do have an air of legend about them. Landau wasn't just a brilliant physicist.
Yeah.
He was also a renowned teacher, shaping a whole generation of theoretical physicists in the Soviet Union. He had a very particular, and some might say demanding, approach to training young minds.
So what exactly were these 10 Commandments of physics? Were they like the rules for unlocking the secrets of the universe?
Well, not quite rules, but more like a way for Landau to encapsulate his most significant scientific achievements.
Okay.
Imagine 2 stone tablets, like those Moses brought down from Mount Sinai.
Right. Instead of religious pronouncements, they held Landau's key physics discoveries.
Okay, I have to know, what was on those tablets? What physics pronouncements earned a spot in Landau's top 10?
The tablets contained his most groundbreaking work. Things like his theory of superfluidity in helium-2,
Right.
his work with Ginzburg on superconductivity, his theory of Fermi liquids, his contributions to quantum electrodynamics,
Wow.
and even astrophysics. It was a pretty impressive list,
Oh, yeah.
reflecting the breadth and depth of his impact across various fields of physics.
It's like he wanted to solidify his place in the history of physics, ensuring that his contributions would be remembered and celebrated.
And rightfully so. His work revolutionized our understanding of the universe,
Yeah.
especially at the most fundamental level. But his legacy extends beyond his own discoveries.
Yeah.
He was passionate about nurturing future generations of physicists, and that's where his theoretical minimum program comes in.
You mentioned earlier that this program was demanding. What did it involve? Was it like a secret society of physicists?
With initiation rituals and secret handshakes.
Huh? No secret handshakes. But it was quite rigorous.
Huh.
Landau firmly believed that every theoretical physicist, regardless of their area of specialization, should possess a strong foundation in all areas of physics.
Okay.
To ensure this, he designed a challenging exam
Yeah.
called the theoretical minimum.
So it was like a physics boot camp, separating the truly dedicated from those who just dabbled.
In a way, yes.
Okay.
Passing Landau's theoretical minimum exam was a badge of honor,
Wow.
a testament to one's mastery of fundamental physics concepts. Only a select few made it through this trial by fire.
I can only imagine the pressure. But I bet those who succeeded felt incredibly accomplished, knowing they had met Landau's high standards.
Absolutely. Those who passed became part of an elite group, joining the ranks of Landau's students, and they often went on to make significant contributions to physics themselves,
Wow.
carrying the torch of Landau's legacy.
That speaks to his effectiveness as a teacher.
Yeah.
Not just making groundbreaking discoveries himself,
Right.
but also inspiring others to do the same.
Exactly. And his impact on physics education didn't stop there.
Yeah.
The article mentions his famous course of theoretical physics,
Okay.
a monumental 10-volume series co-written with his student Evgeny Lifshitz.
So this textbook series was another way he shaped the landscape of physics education.
Absolutely. It became an essential resource for physics students around the world.
Wow.
Renowned for its rigor, clarity, and comprehensive coverage of theoretical physics, it's actually still in print today,
Really?
a testament to its enduring value and Landau's enduring influence.
It's incredible how he managed to translate his deep understanding of such complex physics into a text that's accessible and impactful for generations of students.
Landau had a gift for simplifying complex ideas, distilling them to their core essence, and making them understandable to others. It's part of what made him such an exceptional teacher and communicator.
So after this deep dive into the world of low-temperature physics and Landau's remarkable life,
Right.
what are the key takeaways for our listener?
Well, I hope our listener leaves with a sense of awe at the strange and beautiful world of quantum mechanics, a world that reveals itself most dramatically at extremely low temperatures. The phenomena we've discussed, superfluidity, superconductivity, and the behavior of Fermi liquids, all challenge our classical intuition and demonstrate the power of quantum mechanics to govern the behavior of matter in ways we never anticipated.
And Landau's story, his relentless pursuit of knowledge, his unique approach to problem solving,
Right.
and his dedication to fostering the next generation of physicists is truly inspiring.
Yeah.
It highlights the importance of curiosity, rigorous thinking, and a passion for unraveling the mysteries of the universe.
Absolutely. And I'd like to leave our listener with one final thought to ponder.
Okay.
If such counterintuitive behaviors can emerge from the microscopic world, what other surprising quantum phenomena might be lurking at the boundaries of our understanding, waiting to be discovered?
That's a great question. It's a tantalizing question to consider. Perhaps our listener will be inspired to delve deeper into these mysteries, explore the uncharted territories of physics, and perhaps even contribute to the ever-evolving tapestry of scientific knowledge.
Who knows? Maybe one day their name will be etched on those physics tablets, alongside Landau and the other giants who dared to explore the universe's most fascinating corners.
Until then, stay curious, keep exploring. And thanks for joining us on this incredible deep dive into the mind-bending world of low-temperature physics and the legacy of Lev Landau.